Let's talk about logarithms. So logarithms are the inverse of exponentiation or exponents. So just to recap on what an inverse is. If we have a function f of x, and I set up a table here. When x is equal to 1, the y value is equal to 2. When x is equal to 2, the y value is equal to 4, and so on. Well, the inverse of f of x, well, what happens is when a function is an inverse of another function, well, it's basically the x and y values you'll notice here, they're just swapped. So when a function is an inverse of another function, the x and y values are swapped. So in our original function, when x is equal to 1, the y value is equal to 2. However, in our inverse function, you'll notice how when the x value is equal to 2, the y value is equal to 1. And you notice how it's like all these values in our table have swapped. Right? When x is equal to 3, the y value is equal to 5 in our original function. And in the inverse function, when x is equal to 5, the y value is equal to 3. So that's just a quick introduction. Now, we're going to be focusing on how to solve simple logarithmic equations. So let's just talk about some features of logarithms. So all logarithms have something known as a base. So this right over here is the base of our logarithm. And logarithms are written in this form, where you have this log symbol, you have a base of the logarithm, which is this number beneath the log symbol, and you have a number next to the base, number above the base, which is usually written in parentheses. And because this is an equation, it's going to be equal to some number. So how do we solve this? Well, it turns out that you can take a logarithmic equation like this, and you can turn it into an exponential equation, something like this, where you have the base of your exponent raised to some power is equal to the answer. Now, how do we do this? So the first step, well, what you're going to do is you're going to take the base of the logarithm and you're going to make it into the base of your exponent. Then you're going to take the answer, and this is going to become the exponent. So the answer becomes the exponent, and it's going to be equal to the thing inside the parentheses. So right over here, this equation right over here on the top, where we have log base 2 of 4 is equal to x. Well, this equation up top, you can actually convert this into 2 to the x power is equal to 4. And obviously, 2 to the second power is equal to 4. So x has to be equal to 2. Now, we're going to be doing a lot more examples. So, might be confusing at first, but let me give you another equation. So, let's say we have log base 3 of 9. And this is going to be equal to some value, x. How do we solve this? Well, we can rewrite this into an exponential equation. The base of our logarithm, which is this number beneath the log symbol, becomes the base of our exponent. This x right over here becomes our exponent. So the thing on the other side of the equation becomes our exponent, and the number inside of parentheses becomes our answer. So now this right over here, this scary looking equation, is actually the same thing as this more friendlier looking equation, right? You have the 3, this turns into the exponent, the base turns into the base of the exponent, the answer right over here turns into the exponent, and then the thing inside the parentheses turns into the answer of our exponential equation. And obviously 3 to the second power is equal to 9, therefore x is equal to 2. Now let's do another one. Let's say we have log base, let's say 4 of 64. And this is going to be equal to some number. The base of our exponent the base of our logarithm turns into the base of our exponent. This answer right over here turns into our exponent. And the thing inside of parentheses turns into our answer. So now we have this brand new equation. These two equations are equal to each other, and log base 4 of 64 is equal to x can actually be converted into this equation, which is 4 to the x power equals to 64, and x is equal to 3. 4 to the 3 power is equal to 64. So those are just some simple logarithmic equations, and this process where you take a logarithmic equation, convert it into exponential equation makes it pretty easy to solve these types of equations. So whenever you're dealing with logarithms, you're never going to see a situation where there's a negative inside the parentheses of this logarithm, or you have a negative base. When you're dealing with logarithms, the base of your logarithm should be greater than 0. It should not be negative. And the thing inside of parentheses should also be greater than 0. It also can't be negative. And the reason why? Well, you're going to be dealing with complex solutions if you have a negative base, or if you have a negative thing inside your parentheses. For example, log base 2 of negative 1 is equal to x. Let's convert this into an exponential equation. So right now, remember, the base of our logarithm becomes the base of our exponent. The answer becomes the actual exponent, and then the thing inside parentheses becomes our answer. So we have this equation. 2 to the x power is equal to negative 1. And it turns out that x has no real solutions. You can try, plug in any numbers. Let's say you plug in x is equal to negative 5. Well, this is the same thing as 2 to the negative 5 power is equal to negative 1. And this is equal to 2 to the negative 5 power is equal to 1 over 2 to the 5th power is equal to negative 1. And what you'll always notice is that this part right over here, whatever x value you plug into this equation, this side of our equation is always going to be positive, while this negative 1 side, well, it's always going to be negative. So this side of our equation is always positive. It doesn't matter if you plug in x is equal to negative 6, negative 7. This equation, this side of the equation is always going to be positive, and it's never going to be negative. So therefore, this equation doesn't have any real solutions. And actually, let me just use Desmos here. So we have 2 to the x power. Let's say we have y is equal to 2 to the x power. And in the other one, we have y is equal to negative 1. And you'll notice how these two graphs, they have no intersection points at all, meaning that there's no solution, right? If you have two graphs like y equals 2x plus 3, and y is equal to, let's say, negative 2x plus 4, what you'll notice is that these two graphs have a solution point, which is this intersection point. However, the graphs I showed you before, they have no intersection point. It goes on forever and forever. So let's talk about some logarithm properties. So let's say if we have log base a of m, and we add this to log base a of n, well, this is just going to be equal to log base a of m times n. So if you have two logarithms where the base of your logarithms are the same, and you're adding these two logarithms together, well, the result is just this single logarithm with the same base, except that you just multiply the things inside the parentheses together. For example, if you have log base 2 of 4, and you add this to log base 2 of 2, what you just do is you keep the same base as your answer, but what you do is you multiply the things inside the parentheses together. So this is just going to be equal to log base 2 of 4 times 2. And this is just equal to log base 2 of 8. Let's do another one. Let's see if we have a log base 3 of, I don't know, let's see, 4. And you add this to log base 3 of 5. Well, what you do is, because the bases of the logarithms are the same, you keep the base. So our answer is going to still have this log base 3. Keep the base. And what you do is you take the things inside the parentheses, take this 4, and you take this 5, take things inside the parentheses, and you multiply it together. So this is just going to be equal to log base 3 of 20. And it turns out that you can do this for pretty much, as long as you want. For example, what I mean by that is, let's say if we have log base 2 of 2, let's say we add this to log base 2 of 3, and then we add this to log base 2 of 4. What is this going to be equal to? Well, you're going to keep the base. So it's still going to be log base 2, and you're going to take everything inside the parentheses. So you're going to take this 2, you're going to take this 3, you're going to take this 4, and you're going to multiply it by each other. So what I mean by this is just that as long as the bases of our logarithms are the same, you could pretty much do this forever, actually. So you just multiply the things inside the parentheses, and in this case, you're just going to get log base 2 of 24. And now the nice thing about this logarithm product rule is that you're able to go backwards as well. So not only are you able to go from log base a of m plus log base a of n, and you multiply these things together, well, you're able to go backwards as well. So for example, if you have log base 2 of 24, and this is just going to be equal to log base 2 of 4 times 6. The thing inside our parentheses is still equal to 24. So these two things I've highlighted have the same value. And what you're able to do is, now you'll notice how our logarithm is in the form of log base a of m times n. And now you're able to convert it into two logarithms. This is just going to be log base 2 of 4 plus log base 2 of 6, right? Log base a of m, log base 2 of 4, plus log base a of n, log base 2 of 6. Let me just show you another examples of this. So let's say if we have log base 3 of 9. Well, we know that 9 is equal to 3 times 3. Log base 3 of 3 times 3. And now you notice how we are in the form of log base a of m times n. So this is just going to be equal to log base 3 of 3 plus log base 3 of 3. I'll just do one more example. Let's say if we have log base 2 of 16. We know that 16 is equal to, well, one option we can do is 8 times 2. 16 is equal to 8 times 2. So this is just going to be equal to log base 2 of 8 plus log base 2 of 2. So yeah, you can go from these two logarithms, this one logarithm, or you can go from this one logarithm, separate the thing inside the parentheses into one factor pair, and then separate the two logarithms, separate it into two logarithms like this. So basically all we did was we kind of separated all of these log things into their own separate equations. And in this first one, we got that x is equal to 4. So x is equal to 4. So that means we were able to substitute 4 instead of log base 2 of 16, because we said that log base 2 of 16 is equal to 4. So we substitute that in. We saw that y was equal to 3. So that means instead of log base 2 of 8, we are able to substitute 3 in for log base 2 of 8. This one, 2 to the first power is equal to 2. So z is equal to 1, which means that instead of log base 2 of 2, we can substitute in a 1 for this. So 4 equals 3 plus 1. So next thing I'm going to be talking to you about, next logarithm property, is this. This is called logarithm quotient rule. And we have log of, let's say, one thing divided by another thing. Let's say log base a of m divided by n. Well, this is just going to be equal to log base a of m minus log base a of n. So this is actually pretty similar to the logarithm property we talked about before. Instead of multiplying, now we are dividing, and then instead of adding, now we're subtracting. That's basically the difference. So if you have something like, let's say, a log base 2 of 4, and you subtract this from log base 2 of 2, well, what you're going to do is you're going to keep the same base, right? You notice how all of these things have the same base. So you're going to keep the base. So there's going to be log base 2. And then what we're going to do is you're going to take the first thing inside of parentheses, make it a numerator, take the second thing inside of parentheses, and then turn it into the denominator. So this is just going to be equal to log base 2 of 4 divided by 2 is 2. Let me just do another example. Let's say if we have log base 3 of, let's say, 12, subtracted by log base 3 of, let's say, 4. Well, what you're going to do is you're going to keep the base. You're going to take the first thing inside of parentheses, and you're going to make it the numerator. You're going to take the second thing inside of parentheses, you're going to make that the denominator. So this is just going to be equal to log base 3 of 12 divided by 4 is 3. Why did I write 12? It's just going to be 3. And it can go the other way. It can go the other way as well. For example, if we have log base 2 of 8, well, we know that 8 is equal to 16 divided by 2. And then now we can use our logarithm quotient rule. So now we have log base a of m divided by n. This is just going to be equal to log base 2 of 16. And then you just subtract it by log base 2 of 2. So yeah, I'm just showing you examples of where you can go from this direction to this direction, or you can go from this direction back to this direction. So log base 2 of 16 over 2. And then this numerator part comes first, and then the denominator part comes second. And everything has the same base, of course. Now, another property of logarithms is you're able to take exponents for the thing inside of the parentheses, and you're able to sort of drop it down. So what I mean by that is if you have log base a of b to some power, well, this is going to be equal to the power, so you kind of bring the power down from the parentheses, times log base a of b. So seems confusing at first, but it's actually pretty simple. So what you do is, let's say if you have log base 2 of 5 to the second power, what you're able to do is you're going to take the exponent and you're just going to drop it down. So this is just going to be equal to 2 times log base 2 of 5. So we just basically took the exponent, we put it down, and then we added this multiplication sign. Let's say we have log base 3 of 3 to the second power. Well, what you're able to do is you're going to take the exponent and you're basically just going to drop it down. So this is going to be equal to 2 log 2 times log base 3 of 3. You just drop down the exponent, so the exponent's not there anymore, and then it becomes this thing that you're multiplying by. And likewise, if you have something like 5 times log base 2 of 3, the opposite is true. What you're able to do is you're able to take this 5 and you're able to turn it into an exponent. So this is actually equal to log base 2 of 3 to the 5th power. This is the opposite of what we did. We're able to take the thing that we're multiplying the log thing by, and we're able to turn it into the exponent. So yeah, that's another property of logarithms. You're able to take the exponent and you're able to sort of bring it down so that you're multiplying by the exponent. Or the opposite can be true. You're able to take the thing that you're multiplying the log by and you're able to turn it into the exponent. Now, the next two logarithm properties are pretty straightforward. So one of it is that if you have log base a of 1, this is always going to be equal to 0. So if you have log base a of 1, it's going to be equal to 0. Now, why is this true? Well, let's rewrite this as an exponential equation. So the base of the logarithm becomes base of exponent, the answer becomes our exponent, and then the thing inside of parentheses becomes our answer. So we get this equation. A to the 0th power is equal to 1. And it turns out that any number to the 0th power is equal to 1. 3 to the 0th power is equal to 1. Doesn't really matter. So if I have something like log base 3 of 1, and I want to find out what this is equal to, well, it's just going to be equal to 0, because 3 to the 0th power is equal to 1. Doesn't matter. It could be 4, 5, 6, whatever. Because it's always raised to the 0th power, it's always going to be equal to 1. And another logarithm property, this one's also a pretty straightforward one. So if you have log base, let's say a of a, it's going to be equal to 1. For example, if I have log base 4 of 4, and I wanted to find out what this was equal to, well, if we rewrite this as an exponential equation, this is the same thing as 4 to the x power is equal to 4. And obviously, 4 to the first power is equal to 4. So x has to be equal to 1. So yeah, log base a of a is equal to 1 because any number to the first power is equal to itself. Any number to the first power is equal to itself. The next two log properties are very important, especially in solving equations. Actually, the next three. So let's say if we have log base x of x to the y power. And we want to find out what this is equal to. Let's say this is equal to z. Well, using our log properties, right, we turn this into exponential equation. So the base of our logarithm becomes exponent. The answer becomes our exponent. And then the thing inside our parentheses becomes the answer. So you can see how if we have log base x of x to the y power, and it's equal to, let's say, z, you'll notice how we end up with this exponential equation. We end up with x to the z power is equal to x to the y power. And from this, we can just conclude that z is equal to y. If both the bases of our exponents are the same, and these two things are equal to each other, well, the exponents have to be the same as well. It's like if you have, let's say, 3 to the first power is equal to 3 to the z power, you know that z is equal to 1. It's sort of like that thing. So just from this equation, I can see that z has to equal to y in order for this equation to be true. So we said that if we have log base x of x to the y power is equal to z, well, instead of a z now, we know that z is equal to y. So we can substitute a y instead of a z. So this is equal to y. Log base x of x to the y power is equal to y. And this is a pretty useful theorem. It's a pretty useful rule. So if we have something like a log base 3 of 9, let's say, and we want to find out what this is equal to, well, we know that we can rewrite this as log base 3 of 3 to the second power. Right, 9 is 3 to the second power. And you notice how, well, it's in the form of this. So what you're able to do now is you're able to say, okay, this is just going to be equal to 2. If you have log base x of x to the y power, you're just going to be left with the exponent. So if the base of your logarithm is equal to the base of the exponent, well, the answer is just going to be the exponent itself. So let me give you another example. So if you have log base 4 of 16, what does this get equal to? Well, you know that 16 can be written as 4 to the second power. And now you'll notice how the base of our logarithm is the same as the base of our exponent. So this is just going to be equal to the exponent itself, which is 2. And the way I like to do this is I like to kind of cross out this. I like to kind of cross out like that. So you're just left with the exponent. Okay, I'm going to be doing a proof now. And my proof, I'm trying to prove that if I have a to the power of log base a of b, well, this is just going to be equal to b. So for example, if I have, let's say, 3 to the power of log base 3 of 4, well, my answer is just going to be 4. So it's just going to be the thing inside of parentheses. So let's say if I did not know that this was equal to the thing inside of parentheses. Let's say this is just equal to some value. Let's say x. Well, what I'm going to do is I'm going to let y be equal to log base a of b. So I'm going to let y be equal to all of this stuff right over here. So I'm just going to rewrite the equation. I'm going to say that a to the y power is equal to x. All we did was substitute in y for all of this stuff. And now you'll notice how we have this exponential equation. And just like how we can convert logarithm equations, so if we have, let's say, a log base b of a is equal to x, and we can convert it into an exponential equation, b to the x power is equal to a, we can do the opposite. We can take an exponential equation and we can turn it into a logarithmic equation. So how do we do this? Well, first we gotta start out writing the log symbol. The base of the exponent becomes the base of the logarithm. The thing on the other side, the thing that it's equal to, becomes the thing inside the parentheses. And the exponent that this base is raised to becomes our answer. So we get that log base a of x is equal to y. Now what you'll notice is that we know that y is equal to log base a of b. So we can substitute that back in for y. We can say that log base a of x is equal to log base a of b. And now what do you notice? Well, in order for these two equations to be true, x has to be equal to b. If these two logarithms, they have the same base and they're equal to each other, well, the things inside the parentheses must also be equal to each other. So now that we proved that x is equal to b, if we go back to our original equation, instead of the x here, let's substitute that with a b. So instead of x here, let's substitute this with a b. And boom, the proof is done. We just proved that a to the log base a of b is equal to b. So once again, if I'm going to do another example, if I have something like 4 to the log base 4 of 3, and I want to find out what this is equal to, well, if the base of the exponent and the base of the logarithm are equal to each other, it's just going to be equal to the thing inside the parentheses. So if I have something like 5 log base 5 of 10, this is just going to be equal to 10, the thing inside the parentheses. The last logarithm property is called the change of base rule, and it's probably by far the most important logarithm property. So let's say if we wanted to evaluate what log base 4 of 6 is equal to using a calculator. If you have a TI-84 calculator, what you can do is you can press math. You're going to scroll all the way down until you see A, which is log base, and you can enter the stuff in, and you get the answer. But the problem is that some calculators don't have this feature. See, TI-84 Plus, you can use log base to basically solve a lot of log problems. But the problem is that a lot of calculators, and some teachers might actually give you those calculators, they don't have log base, and you're stuck with this regular log. So how would you solve log base 4 of 6 if you didn't have this log base feature on your calculator? How would you find out what that's equal to? And just before we do that, just a reminder that whenever you see this log symbol on the calculator, so it seems like it has no base at all, this logarithm. But it turns out that this log thing you see on your calculator, it's in base 10, meaning that it's log base 10. So for example, if I do log of 100, I'm going to get 2. And the reason why is because, well, this is in log base 10. So 10 to the second power gives you 100. If I put in 1,000, I will get 3, because 10, which is this invisible, in this case, this calculator doesn't have base 10, doesn't put it base 10 here, but you can think about it as an invisible 10 here. 10 to the third power is equal to 1,000. And that's what I have written here. 10 to the third power is equal to 1,000. So yeah, the main thing to know is that the log feature in their calculator is just in base 10, if it doesn't say anything there. Now, what the change of base rule does is it allows you to write logarithms in any sort of base. So for example, this is actually the change of base rule. So if I have log base a of b, I can rewrite this as log base c of b divided by log base c of a. So for example, if I have something like log base 5 of 7, I'm able to rewrite this as log of 7 divided by log of 5. So the thing inside of parentheses is always in the top, and the base is always on the bottom. And the OP feature about the change of base rule is that you're able to use any base you want as long as the bases are equal. So log base 5 of 7 is equal to log base 4 of 7 divided by log base 4 of 5. Or you can use 10. You can use pretty much any number as long as it's positive. So this is equal to log base 3 of 7 divided by log base 3 of 5. This is equal to log base 10 of 7 divided by log base 10 of 5. And you'll notice how you can kind of see how useful this theorem is. For example, if I have log base 6 of 8, this is equal to a log. So first I'm just going to write out the stuff we know. Log 6. So remember that the thing inside the parentheses always goes in the numerator, and the base always goes in the denominator. And what you're going to do is you can use any base you want. So log base 6 of 8 is equal to log base. You can do log base 2 of 8 divided by log base 2 of 6. You can do log base pi of 8 divided by log base pi of 6, and so on. So the change of base formula is very useful because it allows you to convert from a base that looks pretty bad to a base that might be better suited for the problem. And so what I'm able to do is I'm able to turn log base 4 of 6, and I'm able to use any sort of base I want for this problem. For example, I'm going to rewrite this using the change of base rule. I'm just going to put it here. Log base a of b is equal to log base c of b divided by log base c of a. So I can rewrite this as log base, let's say 3 of 6 divided by log base 3 of 4. The thing inside parentheses always goes on the top, and the thing inside, the base itself, is always in the denominator, right? The thing inside the numerator is always the thing inside the parentheses, and the thing on the bottom, on the denominator, is always including the thing that was your base originally. So yeah, this is why the change of base rule is important. You can also rewrite this as, let's say, log base 10 of 6 divided by log base 10 of 4. You can use any base you want, you notice. So it can be log base 4 of b divided by log base 4 of a, log base 3, log base 2, whatever your calculator has. You can use logarithms and you can convert it to the base that you would like. In this case, because we're trying to use a calculator to solve the problem, and my calculator is in log base 10, which means that I converted my logarithms using the change of base formula into base 10. And now I can use the calculator. So this is going to be log base 10 of 6 divided by log base 10 of 4. And you notice how I get the same answer as if I used log base, right? So yeah, that's why the change of base rule is pretty nice. Let's do another example. Let's say if I have log base 5 of 7, and I want to find out what this is equal to. Without using the log base function on my calculator. So if your teacher doesn't allow you to use this, how would you solve this logarithm? Well, it would just be equal to, I'm just going to put that on the side. This is just going to be equal to log base. Remember, the thing inside the parentheses always goes on the top, and our base always goes on the bottom. And you can use any base you want, meaning I'm just going to use base 10 because that's what my calculator has. Right now, I've rewritten my original expression in terms of base 10, and now I can use the calculator to solve it. You see, my calculator is in base 10, and my problem is using base 5, which is bad. So using the change of base rule, I'm able to convert this logarithm into base 10. So now I can use my calculator to solve this. So I'm going to use my calculator. This is just going to be equal to log base 7, log base 10 of 7, divided by log base 10 of 5. Log base 10, there's an invisible 10 here. Just pretend there's an invisible 10 there. Log base 10 of 5. And you notice how it's the same answer as if I actually used the log base function. You notice how it's the same answer as if I used log base function like that.